Okay. So yeah, thanks for the invitation. Okay, good evening to everyone. And I'm going to talk about pricing option on flow forwards by neural network in Hilbert spaces. And this is a joint project, my collaboration, Fred Espenbent and Niels Dettering. So I will give just a short introduction and motivation. There's some abstract results that are a bit mathematical, but I will try to keep the level as low as possible. Then I will talk about energy market and option in energy market. And finally, I will give some implementation, some numerical implementation and the result that we get with our neural network architecture. So let's get started. So let me recall what is a neural network. So let me give a mathematical description of the classical neural network. Basically, a neural network is defined by a continuous nonlinear function sigma, which is the activation function. There is some vector A in Rn and some scalars, which call L and B. And so a neuron is N, L, A, and B is simply a continuous function from Rn, the input space, to the real number, which is defined in this way. So you have the input X, we do an affine transformation, we get a real number, we compose with the activation function, we still get a real number, and then we multiply by this scalar. This is a neuron, and so a one-layer neural network, and N for short, is simply a finite sum of neurons. So I take all these neurons with different weights, I sum up, and this is my one-layer neural network. And a classical result, which goes back to the 80 and was due to Saibenko first, is the so-called universal approximation theorem, which basically, what does it say? It says that we have to find condition on the activation function sigma such that the following must hold. Basically, if I have a continuous function from Rn to R, some compact set where I want to approximate my function, some error epsilon, then there exists basically some m neurons with some weights, such that if I compute the difference between the function that I want to approximate with my one-layer neural network, then the error that I could meet is at most epsilon, is under control. And this is the classical universal approximation theorem for function from Rn to R. Okay. Now in this talk, now we are going to discuss about infinite neural network in infinite dimensions, so beyond Rn. So the first question is why one should go beyond Rn and not let's just stick to the finite dimensional space. Well, let me start with the slogan that functional data is everywhere in finance. For instance, stock prices, volatility surface, and so on. So the main goal of our architecture is that we want to learn function whose input is itself a function, so is an infinite dimensional object. And the application we have in mind, and we are going to show you later, for instance, if you consider energy markets, there are traded forwards for different maturity. And it's common to trade option written on this forward. Empirically, one observes a large degree of idiosyncratic risk across different maturities and also a clear correlation structure. And so many people in the last decades in academia have tried to modelize this phenomenon. And so one possibility is to model the forward curve via an Hilbert space value process. What does it mean? The state variable which describes my system, let's call it xt, is an element of some function space H. So it's an infinite dimensional object. Later I will specify what is this H. And so if one agrees to use this model, which comes from mathematical finance, then a European option on the forward can be seen. Then we want to price these options. That's the fair value of the option, the price. Then the price function V can be seen as a function which goes from this infinite dimensional vector space to the real number. And so now the goal is to somehow to learn this function, to approximate this function with suitable neural network. And also we have, these are current projects we are working on, but we are not going to discuss about this this evening. We want to use our infinite dimensional architecture to do high frequency trading and limit order book dynamics, and also to solve a numerical solution of partial differential equation. These are working in project, but okay, we are not going to discuss about this. This evening we will discuss about energy markets. Okay, now we become a bit more technical. So, okay, so let's give me an outline of your result. We have H is an Hilbert space with basis AK. Okay, if you know what is an Hilbert space, it's fine. If not, I will explain now. Basically, Hilbert space, okay, if you are in Rn, you have, a point in Rn is specified by n coordinates. In Hilbert space, basically, if you have a point in Hilbert space, this point, let's call it x, is specified by the infinite number of coordinates xk. So like in Rn, I can expand my vector like according to these spaces, like a linear combination. If you were in Rn, this sum would go from k to 1 to n. Here we have an infinite bunch of coordinates, so we have to the sum run to infinity. And the same for the second point. But okay, the important part, we can define a scalar product. And it's like in Rn, because if we had n coordinate, this would be exactly the scalar product in Rn. And the same, we can define a norm. Okay, here we just need a bit of notation. H prime denotes the space. So we have this Hilbert space. Now, this H prime is what? Is the space of linear and continuous map L from the space itself to R. And LH is the space of linear and continuous map A from H to itself. So if you were in Rn, basically, this is the space of matrices, n times n matrices. Here we are in infinite dimension. You can think to this space like the space of infinite dimensional matrix with, infinitely many rows, infinitely many columns. Okay, now we want to define an infinite dimensional neuron. So we modelize this neuron to the classical neuron that I showed you before. So before we had this affine function, right? We take the input, we multiply by a vector plus a scalar. And now we replace this with this affine transformation. So X, which is in H, we multiply by an infinite dimensional matrix, and then we sum up an infinite dimensional vector. Then after that, we replace the nonlinearity sigma with a nonlinearity which goes from the space H to itself. And finally, we compose with a linear and continuous form, which goes from H to R. So more concretely, a neuron with weight L, A, and B is this function. So we take H in X, in our Hilbert space, an infinite dimensional vector. We do this affine transformation, we are still in H. We compose with sigma, we are still in H. And finally, we compose with L and we get a real number. So we go from H to the real number. And this is our neuron with weight L, A, and B. And now the result that we got, and I'm going to show you briefly, is an abstract universal approximation theorem in the same spirit of the previous approximation theorem in finite dimension, and an approximation with finite dimensional maps. I'm going to show you what I mean soon. Okay, so some results. Okay, the nonlinearity sigma must satisfy some suitable condition that I'm not going to spell out now, but okay, it must be a quite nice function, but actually we have a wide class of nonlinearity that are suitable. Okay, let's take this activation function. Then you give me a continuous function from my Hilbert space to the real number, a subset where I want to approximate my function, k, an error. Then, as in the classical case, there exist m neurons with some weights, right? This is the weights that characterize my neuron, such that if I sum up these m neurons, then the difference, the error that I commit when I try to approximate my function is at most epsilon, uniformly on my subset where I want to learn my function. It's the same like in the finite dimension. The only difference is now that x, this point, is an infinite dimensional vector. It's not anymore in Rn. And this is the abstract universal approximation theorem. Now, what about the finite dimensional approximation? Okay, again, take a vector in the Hilbert space. So we have infinite bunch of coordinates. So we fix an integer n. We define the n orthogonal projector, which is this map. Is pi n, which goes from the Hilbert space to the span. So you take the linear combination of the first n vector of the basis. So what do we do concretely? We have this vector, so with infinite many coordinates. Basically, here you see we get rid of all the coordinates bigger than n. So we truncate this sum to n. So we are projecting indeed the first n elements of this on the first n elements of the orthogonal basis. So we got this. And now we have this result, finite dimensional approximation. So suppose we have an epsilon, which is a neural network coming from the previous theorem. So we have some neural network which can approximate quite well, I mean, uniformly, I mean, with an error at most epsilon, our function that we want to learn. Now fix a second error. Then for all n big enough, actually, in turn, I can approximate arbitrarily well my original function with this new architecture. Okay, I agree that this expression looks a bit mysterious. I will go through the details later when we do application. But I mean, for the moment, believe me, this architecture is not so different from the standard architecture you're used to, because I mean, all these quantity appearing here basically are finite dimensional. So I will explain this more in detail later with the application. But so, for instance, this quantity now is a matrix, is a finite dimensional matrix. So something that you can implement in a machine. And so basically, this theorem tells us if we can approximate from the beginning a function with an infinite dimensional neural network, then actually in turn, okay, the error increases a bit, but we can approximate our original function with almost, I mean, with an almost classical neural network. And later I will explain more in detail the structure of this neural network. But these things is something that you can implement in a machine. That's the important part. This you cannot implement because, I mean, how can you plug in a machine an infinite dimensional vector, so an infinite amount of number? You cannot. But in this case, you can. And this is crucial for application. But okay, more details later. So to sum up, so far we have learned that we can approximate arbitrarily well function from infinite dimensional vector space to R via sum of infinite dimensional neurons. And then we can in turn approximate infinite dimensional neurons via almost classical architecture. And so we can implement those things in a computer. Okay, now let's talk about, these are the abstract results. So now let's talk about application in energy market. So let's discuss a bit about energy market first. So in electricity market, one trades option on forward contract, which delivers power of a period of time. So for instance, you have some contract which I agree to sell electricity, let's say, over a period, let's say from the 1st of July to the 1st of August, because electricity is a so-called flow commodity. I cannot sell electricity for an instantaneous time. By definition, I can sell electricity only on a period of time. So let's say from 1st of July to 1st of August. Okay, so we have this forward contract. So we denote by F at T1, T2, I mean, the price of the forward at time T. Okay, as usual, when you do mathematical finance, when you want to construct a model, I mean, you want to construct a model that is arbitrage-free. And so the standard way to do this, I mean, people in academia, when they were studying this kind of forward contract in the electricity markets, I mean, the trick is to turn this quantity in this way. So what is it? The basic idea is we want now to modelize this quantity, which at the moment is a bit mysterious, but later will be clear. But suppose we can modelize this, so as a stochastic process labeled by time t, in some function space. Suppose we are able to do this, then okay, once we have this, we integrate with respect to psi, the time to maturity, and we recover the forward price that we are interested in. So from now on, we will focus only on this object, because once we have this object, then we can, by integration, we can recover the price we are interested in. Okay, so, okay, now don't be scared about this expression. I will explain what do I mean, but we do not need to go into details. So, okay, as I said, we need a state space, H, an Hilbert space. And this is the so-called Filippovich space. For people working in interest rate theory, this should sound familiar. But in any case, what is this space? It's a space of function from 0 infinity to R, let's call it X, such that they satisfy this condition. So I take the derivative, I square it, I integrate with respect against the exponential function, and this quantity must be finite. And this actually, it turns out that it is a Hilbert space. But so it's an infinite dimensional vector space because it's a space of functions, so you have infinite many coordinates. This is our state space where the process will live. And now we need a dynamics. So we need this. We assume that the log forward y satisfy the following stochastic partial differential equation. Okay, probably you have never seen maybe a stochastic partial differential equation, but it doesn't matter. Probably you're familiar with Black-Scholes model, and Black-Scholes model is based on the geometric Brownian motion. So postulate that the asset prices follow some stochastic dynamics. Here, basically, is the same. It's a bit more complicated, but the idea is the same. We suppose that a log forward curve, let's call it Y, satisfies this stochastic dynamics. So as initial condition at 0, it must be equal to Y, where Y is an object of the Fibonacci space. So it's a function, Y is a function which satisfies these things. And then we make evolve this. So this is the initial term structure, is a curve. We have a forward curve. And then we make evolve randomly in time this Y, and we get a forward curve, how it evolves, let's say, in 1 month, in 2 months, and something like that. So once we solve this is the log forward curve, we take the exponential, and we get, finally, our xt psi. So because remember, we were interested in this. Okay, and this is a stochastic process parameterized by time t, and if you fix t and you make vary psi, so you see that this is a function of psi, so and this as a function of psi belongs to our space H, to our Hilbert space. Okay, now we know, so if we can solve this, we have this. And now, okay, we want to price our option. So, okay, let's say we want to price the option today. Let's say t equals 0. We have a European option with maturity tau. So the value, the price of the option can be seen as this function. So let me explain every passage. So first of all, x means that we are considering the forward curve when at 0 is exactly equal to this x, which is in our Fibonacci space. So at 0, it must be equal to x, which is a function in the Fibonacci space. So what do we do concretely? So we pick a function in H. Okay, we can take the log is still a function in H, and now we consider the solution to this SPD with initial datum log x. We make this y evolve. We evaluate this tau at maturity when we have the maturity of the option. Once we have this, okay, oh, sorry, you take exponential, so you recover this, right? And so once you have this, and then what is Q? Q is the payoff of the option, which we do not specify at the moment, is some payoff of the option. So this object is in H, I compose with Q, I get a real number, and finally I take expectation. As usual, when you price option, you're, I mean, if you're not familiar with arbitrage theory, but basically when you price option, you take some the expectation of the payoff according to some probability measure. And so, and this is the value of the option. But so the important part, I mean, that you have to take away from this slide is that, so we start from some infinite dimensional vector x, which is in H, and we get the price of the option. So what you have to take away from this slide is that the option price is a function of the initial term structure x. So the price of the option is a function of an input that is infinite dimensional. It's not in Rn. It is not in any Rn. It is really infinite dimensional. That's what you have to take away from these slides. And so the idea, since now the payoff, the price of the option is in this way, where H is an infinite dimensional space, we want to learn this with our neural network. That's the idea, to get a fair value of the option. So indeed, how to calculate this, the price of the option today, which is a function from our infinite dimensional space to the real number. Okay, for brevity, let's write this as this. I don't want to write every time this. So let's put chi of x is equal to this. So our option price is this, basically. So how can we compute this? Okay, first of all, we introduce a probability measure mu on our infinite dimensional space, which is supported some set. And then we see that the price of the option minimizes the following mean square error. Okay, what do we do? So we take the payoff of the option minus the real price, the fair value of the option. We square it, then we integrate with respect to this measure that we have introduced over our infinite dimensional space, and then finally we take expectation. Well, actually, this thing is equal to the infimum of this thing. So here, instead of V, you plug in our infinite dimensional neurons, right? You compute the same expression, and then you try to minimize when you vary the number of neurons and the number of weights. So you try to minimize this expression when you vary M and the number of, or the parameter of the neurons. Well, actually, when you do this, you achieve the infimum. This expression is equal exactly to this expression where D is the price of the option. So what is the idea? I mean, if we can make this expression very small because we choose suitable weights, right? It means that we are close to this expression. But so it means that this expression, our net, is close to the function V that we want to learn, right? So how do we implement this? Basically, we draw some random samples from our Hilbert space Z1, Zs, according to the law mu, and then we approximate the right-hand side via this way. And we try to approximate this infimum, again, over, I mean, we tune the parameter such that this infimum is close to this. So behind the scenes, we are basically using the strong law of large numbers. Basically, that's the main idea. That's to recover this field. Okay. Okay, we are almost done with the mathematical setup. Then we will swap to practical implementation. Okay, we are in our Hilbert space H. We need to find now a suitable basis because otherwise we cannot do anything. And so we focus, okay, of course, we cannot work with infinite number of functions. We have to truncate at some point, of course. And we choose the first basis of our space, E1, E7, which looks like this. So we have first the constant function and some other functions. So, and okay, this is the expression that honestly, some of them look very ugly, but who cares? The more important part is that if you're working, for example, in interest rate theory, you may recognize that E1 is so-called the level, E2 is the slope of the term structure, and E3 is the curvature of the term structure. So these are interpretive factors. Okay, if you don't work in interest rate theory, okay, this is okay. This is in any case is fine. In any case, so we have chosen this seven element of the basis, this 7 function, and now okay, we want to let's specify our contract. So we want to price a call options with exercise time 1 month. So tau is 1 month on a forward which delivers over a period of again 1 month. So it goes from 1/12 to 2/12. Let's say from 1st of August to 1st of September. So is a European call option. So the payoff is given if K is a strike price, like for standard European call option, is the maximum of 0 and this quantity. Okay, this quantity is the value of our forward contract with the delivery period T1 and T2 evaluated at tau. So tau is the maturity of the option. Is this, and then we subtract, as in classical Black-Scholes, we subtract the strike price. So this is our payoff. And as before, I mean, I'm just recalling for you. So the value of the option, recall, is this the expectation of this payoff. Again, is a function of, I mean, the input X belongs to Hilbert space. So it's an infinite dimensional vector. Now, okay, indeed, we want to learn this function. As I said, we can learn this function only on compact set. We cannot learn the function on all Hilbert space, like in the classical universal approximation theorem. You can learn function only on, let's say, compact set of Rn, not on all Rn. And so, as a compact set, we consider this following 7-dimensional hypercube. So basically, what do? This K7, we consider only the first 7 elements of the basis, and we take linear combination with weight xk, where xk is between -1/2 and 1/2. So basically, you can identify this object with a 7-dimensional hypercube of side -1/2 and 1/2. So we have a 7-dimensional hypercube in R7 now, and we keep this with the uniform measure. And then we are going to sample from this hypercube. Okay, to sum up, so far, what have we learned? What you have to bring home? That the price V of an option on a flow forward is a function of the initial term structure X, which is an infinite dimensional object. So this X cannot belong to any finite Rn. It really belongs to infinite dimensional vector space. And then we can recast the price V, as a solution of an optimization problem. So by drawing random sample from H, we approximate the minimum as I described before. Okay, and now let's see how to implement this concretely. So, and now we are going to do some numerical experiment. Okay, now from the previous theorem, the final dimensional approximation, it says if you give me some error, some tolerance delta, and some non-linear activation function which is suitable, then there exists some new M neurons with some weights, such that for all n big enough, so now the function that we want to approximate, the price of the option, minus this neural network, the error is uniformly over the compact set at most delta. Now it's time to spell out that this actually is a finite dimensional neural network. It's not anymore infinite dimensional. Why that? Okay, we have choose n big enough and choose, let's say, Hn is the vector space generated by the first n vector of the basis, which of course can be seen isomorphic to Rn. So basically you can see this Hn is Rn basically. Okay, and now what happens here? Okay, a priori it seems an infinite dimensional object, but actually it's not the case because we take X, which is, okay, in H. But then we project, so basically after this we are in Rn. Then we compose with a linear map, we are still back to H, but then we project again, we are still back to Rn. So basically here we are going from Rn to Rn. So if A bar J is the restriction of P and J to this Rn, then this A bar J can be, can be seen as a matrix from Rn to Rn. So this thing is not anymore an infinite dimensional quantity, it's a matrix. Again, the same for the idea for this vector. Bj a priori, belongs to H, so is an infinite dimensional vector. But again, we project. So by projecting, we get rid of all the coordinates bigger than n. We are just left with the first n coordinates. So it's a vector of Rn. So let's call it B bar J. So also this vector is in Rn. And the same is true for all these other ways. So in the end, all these quantities are finite dimensional. So in the end, so these things, which is this, can be rewritten like this. And now X belongs to Hn, so Rn. And so the important part is that all quantities appearing on the right-hand side are now finite dimensional. And so we are in good shape because now we can implement this in a machine. How do we do this? Okay, of course, we use Python and we use TensorFlow and Keras library, of course. Okay, but there is one subtlety that in classical neural networks, the output dimension of a node is typically 1. And the activation function is a map which goes from R to R, right? In our case, it's a bit different. So we implement each node with input output dimension n as a Keras layers with n nodes, each with input dimension n and output dimension 1. So this entire layer has exactly the structure of one of our nodes, input and output n dimensional. So, a picture is more explanatory than 1,000 words. So let's have a look at this picture. So what happens? This is our neural network. We have input layers. So we have, these are just numbers. And so this is n-dimensional vector in Rn. So let's consider this first layer. So all this number goes here. So the input dimension of this layer is Rn. The output dimension is still Rn. So and then we are here at the activation layer. The output is still Rn. And now with the linear form, finally, we project to R. So the input is R. And we do the same for all M nodes. And finally, so here we get a real number. We just sum up and we get eventually a real number. So it's a bit different from the classical architecture, but still is almost classical. You can implement with this trick in the Keras library. Okay, okay. Last ingredient. Okay, we remember that we were postulating. So the log forward curve was solving this SPD. So now we have somehow to choose this coefficient and this noise. We have to do some specification. How do we do this? Yeah, okay, basically we choose, first of all, one-dimensional Brownell motion, and then a 7-dimensional Brownian motion, so to see how they behave in a different way. For 1-dimensional noise, 7-dimensional noise. We simulate our SPD with only one simulation, Monte Carlo, and then we get a solution, and we evaluate this solution at tau. So tau, remember, that is the exercise time of the option. And so what is our training set? I mean, at some point, we have to feed in our neural network. So what is the training set? It's the following one. So K7 was our hypercube, right? So we sample 10 million of points of 7-dimensional vector from this hypercube. And so we sample in an independent way and uniformly distributed. So we sample 10 million of 7-dimensional vector from this hypercube. And then we derive the payoff with respect to ZS. So what do we do? ZS, okay, belongs to this, but you know, it also belongs to the Filippi space, so it's a curve, it's a function. As before, so we take this as initial condition, we solve our SPD with initial condition ZS. We can solve this, we simulate this SPD, we evaluate at maturity, tau, and we get, again, a function in H. And finally, as I showed to you before, we take the payoff and we get a real number. So we do this for all training, this point. So in other words, the training set consists of the input-output pairs, ZS, which basically can be, is a function, but can be identified with this 7-dimensional vector, which lies here. And the output is the option payoff with respect to this ZS. Okay, this is the input-output pair. And so we use this training set to fit several neural networks with the number of hidden nodes ranging from 1 to 30. And then, okay, we use a stochastic gradient descent with a batch size 10,000 and 50 epochs. This is just technicalities. What about the test set? Okay, here we do in a different way. We generate a test set of size 10,000. Okay, so we generate, as before, we generate this ZS test. We sample from this 7-dimensional hypercube with respect to the uniform measure. So we sample also in this way. And we get this ZS test, 10,000 of them. And then, as you do in classical pricing model, I mean, to compute now the option price, I mean, we have to compute this in the end. We use, as banks do, we use Monte Carlo simulation. So, I mean, we take ZS test and then we simulate via Monte Carlo, we get an estimate of this, of the price of the option. This, for us, is the real price of the option, is the benchmark obtained via Monte Carlo simulation. Okay, now we have a training set, we have a test set, we can fit our neural network, and then we finally calculate for each of the fitted model the mean square error with respect to the test set and see what we get. Okay, this is the mean square error. Remember that we are dealing with different dynamics, two different dynamics. This is the Brownian motion is 1-dimensional, and this is 7-dimensional. But in both cases, we see that there is the typical Hilbert curve. So this is the mean square error. And okay, except if we discard the network with a very few nodes, and we average out the mean square error, actually in the end, in both cases, 1-dimensional and 7-dimensional, we get an error which is of the order of 10 to the minus 5. And remember this factor, because then we will compare this with classical neural network, and the error that we will get will be much larger. So basically here we get an average mean square error of 10 to the minus 5. Okay, we did several numerical experiments. I mean, this is one of them. I cannot present all of them. And then, okay, what do? We have our neural network, which is now trained and fit. And now we want to compute the option price for an initial curve, such that now, I mean, again, we sample for our 7-dimensional hypercube, but this time we just make vary the first coefficient, and all the other remaining coefficients are set to 0. We can do this, for instance. And then, okay, well, let's see what we get. The green line describes the option price as determined by the neural network, our neural network. And the red stars are basically the test set, the things that you get via Monte Carlo simulation. And you see that in both cases, one-dimensional Brownian motion, seven-dimensional Brownian motion, there is a very good fitting. There is in this case. And then, okay, we have done other experiments, but I cannot present all of this. The last thing that I want to present is a comparison with classical neural network. Okay, let's forget about architecture. Let's go back to classical neural network. So in RD, and let's see how we can price option, and let's see what we get. So we compare the accuracy of our approach to the one obtained with a classical neural network with one-dimensional activation function, and where instead of using the basis coefficient as inputs to the network, we discretize the initial function x on an equally spaced grid. So remember that we have 10 million of samples ZS, which are like this, are function in our Hilbert space, definitive space, right? We sample this coefficient from the 7-dimensional hypercube, and these are the first 7 elements of the basis. This was how we generate our training set. And now, instead of plugging in the neural network as we did before, this coefficient, ZSK, we do a different approach. We do an empirical approach. Basically, suppose we have this, now we have this curve, we sample this function on a grid of equally spaced points. So either 10 or 20. So we choose some either 10 points or 20 points, and we evaluate this ZS at this point. And so now, basically, the input-output pairs is, okay, as before, the output pairs is key z of x, but now the input is what? Is this curve sample of this size 0, size d points, either 10 or 20 points. And we do this for 10 million of times. So this is the input-output pairs in this case. It's like a bank would do. You look at the curve empirically, you sample the curve, and then you feed in this in your neural network. Okay, and then, okay, we feed this classical neural network with a number of hidden nodes ranging from 5 to 150. And when the grid is 10-dimensional, the number of parameters trainable ranges from 60 to 1,800, sorry. And this basically is important because it's a fair comparison, because before in our architecture, the number of parameters that you can train were ranging from 63 to 1,890. So basically, we have the same number of parameters. So it's a fair comparison. Okay, for d equal to 20, you have more parameters. Okay, but in both cases, okay, then we train this classical neural network, and again, we compute the mean square error between the neural network fitted and the test set. And let's see what we get. Well, in this case, okay, we get really a lot of noise. Basically, it seems that, okay, it's not so bad as it looks like, because, okay, there is no clear pattern. There is really a lot of noise. Okay, this is one-dimensional Brownian motion, 7-dimensional Brownian motion. The blue line is when the grid is 10 points, and the orange is when it's 10 points, 20 points. If you compute the average mean square error, in both cases, you get a mean square error of the order 10 to the -3 in all cases, which is, if you remember from before, in our cases, we get an average mean square error of the order 10 to the -5, so a really big improvement. I guess, we are still doing many experiments, but I guess here probably there is some overfitting, because otherwise we cannot explain all this fluctuating behavior, because it seems that we are really catching a lot of noise. But still, so far our network seems promising, but we're still doing many experiments. So to conclude, but probably an explanation why our network somehow produces superior result is that our architecture, our neural network, takes into account structure that does not need to be explained by the net itself. Because indeed, it is constructed in terms of interpretable factors like level, slope, and curvature of the third structure. In other words, E1, E2. So remember that we are considering this. So we take this basis, and these are factors, right? And so basically, the input of the network are the coefficient with respect to this factor. So somehow it seems that in this way, our neural network is not forced to learn this this structure because it's already given to them thanks to our implementation. And also, I guess we are still doing some experiment, but our approach also will pay out in computing sensitivities of the option price V with respect to this factor. Because when you want to compute the delta or the vega or the sensitivity of the option, if you have to use classical neural network trained by sampling, as we did in this last experiment, then it becomes, and you want to compute the sensitivities, the Greeks, then it's definitely not an easy task. With our architecture, I guess it should be a much more easier task. And okay, these are the references. Okay, these are this theoretical paper. This is the second paper is the paper on which this talk was based on. And if you're curious about the code, you can also find the code on GitHub. And yeah, this is the way. If you want to contact me for other questions, yeah, thank you for the attention.